Hello, welcome back. In this segment, I will formally define the meaning of a key exchange experiment. Okay, let's assume n is the security parameter. N could be the key length, for example. Okay, we are talking about a key exchange experiment. KE stands for key exchange experiment. A is an adversary. I will explain the role of adversary in a moment. Pi is some protocol. It could be Diffie-Hellman key exchange that we are trying to understand. Okay, we are only doing an eavesdropping, meaning Alice and Bob can exchange data in a public channel. The attacker can only observe the channel, not modify the channel. That's basically the meaning of eavesdropping. Okay, so A is an adversary, Pi is the protocol. Pi could be Diffie-Hellman, for example. So you can imagine this to be DH. Okay, Pi is DH more concretely. So what is this key exchange experiment? More formally, let us pick a random number B, which could be either 0 or 1. All right. We don't tell that to anyone. We just pick a random number B. K is the output of the key exchange algorithm. Let's say we ran DH, Diffie-Hellman key exchange protocol. And as you may recall, both Alice and Bob will arrive at the same key K. Okay, that's the key K that I'm talking about here. So if our B that we are randomly choosing, let me use notation R here to say randomly choosing from this 0, 1 set. If B is 0, we define a new variable K cap to be K, okay, the K that we obtained from the Diffie-Hellman key exchange. On the other hand, if B is 1, 0, 1 power n means you randomly construct a n-bit number and put it into the key K cap, okay? So this is the setup. And now we call the adversary and we pass a few things to the adversary. We pass the key K cap, okay? Adversary doesn't know the B, he doesn't know the key K, of course. He only knows that somebody is calling me, and the K cap is the input. K cap, remember, can be the actual key that we got from Diffie-Hellman key exchange, for example, or it could be a random n-bit number. Okay, the adversary doesn't know that yet. What is this trans? Trans means you can imagine the complete transcript of the protocol. Okay, since the adversary is allowed to monitor the traffic, let's say Alice is here, Bob is here, right? They do Diffie-Hellman key exchange by exchanging public messages, right, over the public channel. They do something like this, and they both end up with KK, right? That's something that we learned earlier. So what is this transcript then? Transcript is all the public information, right? Okay, this is G power X from Alice to Bob, and this is G power Y from Bob to Alice. All of these things are public. Okay, G is public, G power X is public, G power Y is public, but not X and Y, of course. The transcript contains all the information like the group, the cyclic group, the order of the group, and so on. All of those things are part of the transcript. All public data. So what is the goal of the adversary? The adversary is trying to figure out whether he is given the key K that we got from the Diffie-Hellman key exchange protocol, or we are given a random n-bit number. Okay. So he's going to output a bit B prime. Again, it belongs to 0 or 1. When will we say adversary wins the game? We say the adversary wins the game if B prime is equal to B, meaning he was able to somehow distinguish between the key that was obtained through the Diffie-Hellman key exchange protocol against the n-bit number, right? If remember, if say B prime is 0 for a moment, so he was saying B prime is 0, and it turned out to be correct, okay, meaning B prime is same as the B that we have gotten here. Okay, when do we get B to be 0? We get B to be 0 if we feed in this key K cap, key K cap, same as the key we obtained through Diffie-Hellman key exchange. Okay, that means there must be something wrong in this protocol where he was able to distinguish this secret key K from uniform looking n-bit data. Okay, that's basically the way to visualize this more intuitively. Okay, so now we can define more precisely what is the probability that a key exchange experiment is successful. Well, you can randomly just say 1 bit, right? It could be correct half of the time. So in cryptography, we define this experiment more formally like this. The probability of the key exchange to be like this: probability with this experiment, right? Key exchange experiment, which I have defined it more formally earlier above. So what is the probability that key exchange returns 1? Okay, the probability that the key exchange algorithm, the key exchange experiment returns 1 only if the output B prime that's coming from the adversary is same as the B that was given. Okay, that was randomly chosen, of course, not given, randomly chosen. So if this probability is bounded by say half plus some small, really tiny value, negligible function. Negligible means you can imagine, let me give an example. Negligible of n means when n is large, the negligible of n is very close to 0. You can imagine, like we say the key exchange algorithm is secure if the probability that an adversary can win the game, meaning he was able to predict whether we are giving him the key from the protocol or from random number, is bounded by half plus a really tiny number, okay, which is a function of n. N is the key size, you can imagine, or security parameter. Okay, so this is the basic framework I will use in my next part of the demo to show to you why Diffie-Hellman key exchange is considered secure. This is how we formally define security of a key exchange protocol. Okay, that's all. Thank you very much for your attention.